Hello everyone and
Okay.
welcome to the 8th of the Alumni Talk series organized by Akash Ganga. We are delighted to have Sujay Mate from the class of 2016 with us today as the speaker. Sujay is a PhD student at IRAP Toulouse. His research focuses on the detection and multi-wavelength observation of gamma ray bursts and high energy transients. Sujay is currently working on the space-based multiband astronomical variable object monitor SVOM, a future gamma ray burst telescope which is scheduled to be launched in 2022. So without further ado, I would like to hand over the mic to Sujay for his talk. Over to you, Sujay.
Okay. Thank you. What's your Kastub, right? I think.
Yeah, I'm Kaustubh.
Yes. Okay. Thanks. So, welcome everyone. So I just realized actually I cannot see the chat and all, and then there is apparently the raise hand option also. So, and I realized from previous talks that there's usually a lot of silence. So I would rather appreciate if you ask questions directly by raising hand and like over voice rather than chat. And it's actually a good exercise for most of you to actually ask questions, because for a certain point in time you will actually attending real seminars. So it's a good practice probably to let go of the fear. With that I will start the talk. So I will mostly talk about the detection of, I will keep the talk is more on the instrument side. So I will just introduce what are gamma ray burst, how the SVOM mission is, how do you detect high energy phenomena like GRBs, and what are how does this SVOM mission will be detecting GRBs, and I will go into details of the instrument I'm working on, and particularly talk about how it works, how it actually detects this radiation from the high energy radiation from the gamma rays. And also I will slightly touch upon my work. I will not go into details, all it is too specific probably for the audience here. So let's first start with what are gamma ray bursts. So as is the name suggests more or less, so they are like very intense flash of gamma rays coming from the sky, and they are so luminous that they are the most luminous explosions in the universe. And for the fraction of seconds when their luminosity is at the peak, you can see on the left that they actually outshine the entire universe at that energy, for example, at least at that particular within the band. So in the left you can see there is the Milky Way and all the gamma ray radiation at one particular energy, and then the peak, when it is at the peak, it literally outshines the entire emission. And so the origin of these objects is into the two types. They're like, one is either due to the compact object merger, which is like two neutron stars or neutron star or black hole, or due to the core collapse of very high mass star, which is more than 15 solar mass, or like very large mass. So these two types are produced. The duration of the GRBs have a kind of this bimodal distribution. If you see in this middle plot, just a second. Can you see? There is a pointer somewhere, right? Yes. Yeah, you can see the pointer, right? I think on the screen. Okay, so you can. There are basically two different types usually give rise to two different types, the duration of the gamma ray burst. So usually the short GRBs, which are about less than 2 seconds, are caused by the compact objects, and then the longer GRBs, which are more than 2 seconds and can be up to 200 seconds or even longer, are thought to be caused by massive stars. So this is like this is like the general dichotomy, but there are now also observations that we have some kind of GRBs which are in between, and also so there can be different types of origins also, like in between something. So this is something which is more or less consensus at the moment. It's a fact, but there are still also it's not a complete divide. The divide is not very sharp, for example. So on the right, in the right figure, you can see the typical scenario. So it doesn't matter what is the origin of this GRB. Usually, even in both cases, the most accepted model is like that. You have a central engine, usually as a black hole, or there are cases observations can be a magnetar also, and then it launches a jet which passes through the surrounding medium, and then you have this first part of the jet when it is in the very dense medium of the star or the collapsed object. You have this prompt emission, which is seen as the GRB, which is the gamma ray flash. And then when this jet goes upward into the interstellar and intergalactic medium, you have these afterglows coming out. It interacts with this medium, and then you have this afterglow emission, which is observed usually at lower wavelength, and also sometimes even at higher, very high energy gamma rays, like of the order of TeV. So if you have the spectrum of the gamma ray burst, you get typical spectrum shown here, like at least in the prompt emission phase, you see that it has a lot of, it spans a really broad range from almost 1 kV. This is 1 MeV 10. Yeah, it's like almost 1 kV to like few MeV. So it's like a broad range. So one fun fact before we proceed is that they were discovered. The gamma ray bursts were first discovered by US military satellites, which were observing it was launched to observe the nuclear peace treaty around the Cold War, and they were observing that there are no tests by any country in the atmosphere, nuclear tests. So those detectors were made to observe these typical signatures, which are of the nuclear tests in the atmosphere, which typically emit gamma rays. But they end up observing gamma ray bursts from the universe in 1970s. And after that, once they discovered, there are a lot of missions have been gone for last 50 years to understand them better. So why do we want to study gamma ray burst? There are multiple reasons. Just a quick intro is that first of all, like they are excellent for astrophysical purposes. Like they are observed at different epochs, in different types of galaxies. Also, they are at the end of they are the really end of the one end of the stellar evolution. So we have a lot of they carry a lot of information about various stages of the how the star dies also, and also if you see the cosmology and also they are observed at different distances, so we can use them to probe the history of the universe, or also the history of the galaxy or star formation rate, etc., etc. Those are like excellent astrophysical in the astrophysical context. And even in the physics side of it is interesting, because they are the densities and at which these gamma ray, like the medium is in the jet is very high, and you have then all sorts of relativistic effects or quantum mechanics or even relativity, gravity, all more or less all fundamental forces of the physics are at play. So they are really excellent in terms of both. So we want to study astrophysics as well as physics. So how do we observe them? So first of all, as I said, like they are in gamma rays. So first thing is we cannot observe from the ground because they are blocked, the prompt emission at least. And and on top of that, they are everywhere, literally in the sky. So it's they are observed from literally in the sky. So you can see here is a plot by Fermi mission, which is also a gamma ray mission. So you can see the gamma ray burst observed by this Fermi, Swift, and Fermi. So you have like they are spread across all the sky, and you don't know where they are coming from, and they are very short-lived. So you want larger telescope. So basically, what you want is a space telescope which is sensitive in gamma rays and X-rays, and also covers broad range of energies, as I showed, because they span a lot of the energies emitted in a very broad range, and you want to detect as many as photons coming from them. You want a good energy resolution, time resolution, because they are short time transients. So you want to detect, don't want to miss anything which is as short as milliseconds also. And we want, again, as I said, a large part of sky, and we want to localize it to the precision also, because the afterglow emission, which we want to study in the lower wavelengths, has to be studied from ground or from other kind of telescope for optical or radio. So we want a very accurate measurement of the location also. So can you do this? Yeah.
Sorry for disturbing. There's a question in the chat.
Yeah.
So Garvit Bansal is asking, is Hawking radiation also a case of gamma ray bursts?
Oh, no, 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 no. No, I don't think so. I mean, I don't really know the details of Hawking radiation, but I don't think so it has to do anything with gamma ray burst. Okay. Okay, where was it? Yeah. So can you observe? So can one telescope give us everything? So the plain answer is no. At least not a space telescope. You can probably build a space telescope, a telescope which gives us this thing, but then you cannot launch it in space. But we want to launch it in space. So how do you do it? So before that, I will just give you a quick review of how do we detect the high energy radiation, because that is important. So what are the types of high energy detectors? So there are like multiple types. So most commonly used are like these CCDs, or planar solid state detectors, which are very good at detecting gamma rays, I mean X-rays or gamma rays also, but they also have some pros and cons. Like CCDs are mostly useful for lower energy X-rays or lower energy X-rays, like up to 10, 20 kVs. Then these solid state detectors, or which are made of cadmium telluride or cadmium zinc telluride, they are very good at higher energies. So I will talk about these in detail a little bit later. And then there are other types, which are like gas proportional counter, which are like gas field detectors, where the interaction is based on the charge field inside a gas chamber, and then the gamma ray or the high energy radiation ionizes the chamber, and you have the detection. And also you have the scintillator types, which are based on plastic scintillator, which creates a light for photoelectric absorption, creates a light, and then inside a crystal, and then you amplify them to this. So these for example are good for higher energy radiation, which is around in the MeV range, for example. So but you also need to localize them. So you need some kind of optics, these kind of things. So you have different kinds of high energy optics also. So for example, you have these focusing optics, which are very good at usually gives you good angular resolution, and they also give you low background. So there are like two types, kind of lobster eye or Walter optics, which are based on grazing incidence X-rays, and you focus them into a plane. But they are usually very bulky in terms of, or complex to manufacture, also restrict field of view. Or you have like non-focusing optics, like coded mask images, which I will talk about in detail at a later time. And also our collimators, which just restrict the field of view. And these are good for they are very simple optics to build, for example, compared to the focusing ones. So what can we do now to detect gamma rays? So one way is that we can do is to take all of these optics on detectors and build one satellite which has different kinds of telescopes doing this with all these all these kind of detectors and optics we have. So we can then cover multiple ranges, angular resolutions, and also good sensitivity. So this is what SVOM will do, for example. So the SVOM is called space astrophysical. Okay, I forgot actually what it's called. Just a second. Anyway, doesn't matter. It's a long acronym which doesn't make much sense. It's called SVOM, Space Variable Object Monitor, if you want to call it that. So it's a French-Chinese mission, and what it will do is that it will have 4 different kinds of telescopes on board in the satellite form, and then there are 3 different types of 3 optical telescope on ground dedicated to GRB observation. So on the satellite, you will have 4 instruments, which as one is this ECLAIRS, which is like the hard X-ray coded mask imager. I'll go into details soon. then which is in the energy range of 4 to 150 keV. Then you have this gamma ray spectrometer, which is in the higher energy range, which is from about 15 keV to 5 MeV. So you cover a very large energy range between ECLAIRS and GRM, for example. And then you have a smaller field of view and little bit more sensitive telescopes in that in terms of localization, which are like MXT, which is the soft X-ray telescope, and then there is a visible telescope also, which will observe in optical channels. So you can have a good localization. So on the right here, for example, you can see the energy range and the energy range and the time response of the instrument. So ECLAIRS and GRM are meant to detect the GRB. Then this MXT and VT will follow up and precise the localization, and that will be sent to the ground. And you have these optical telescopes on ground, which also will follow up this detected GRB. And also you have this GVAC, which can also actually detect a GRB simultaneously with the ECLAIRS. So this type of telescope is already, one of such similar telescope is already there. It's a very excellent one called SWIFT, and it was launched in 2004 and still operational, and it's giving, it has improved our GRB science a lot. It's given a lot of insights. So it has also similar kind of telescopes, and actually a little bit like X-ray and gamma ray camera, like a soft X-ray telescope and a UV telescope. So three telescopes. But it doesn't have a dedicated set of ground-based telescopes. So you have to rely in this case on other observatories to go and follow up this GRB. So that has some problems of following up afterglows. You cannot always follow the afterglows. You also want redshift of GRBs, etc. for studies, and then it's probably not possible to get it always. So SVOM in that aspect is trying to improve this lack of observations, you could per se. So so how will SVOM observe? Usually, as I said, I'll just quickly explain. So usually the ECLAIRS will be like the satellite will be looking in the sky. Then there is a GRB goes up. So the ECLAIRS will detect this GRB on board autonomously. Then it will request a trigger. So it's called trigger. And then it will also request a slew to the satellite. So the trigger will be immediately sent to the ground via some VHF network, and the ground telescopes on the ground, will start to follow up this GRB with the location, which is sent by the ECLAIRS. So the ECLAIRS will localize also at the same time it detects. Then after some time, within like 5 minutes, the satellite will slew, and then so that the GRB comes in the field of view of MXT and VT, and they can start observing at the other two wavelengths. And then simultaneously, it will be created something on the ground. We will create a GCN or VO event, which is a public announcement, basically, that we detected something. And that will be sent to the other telescopes or even other missions, for example, SWIFT or Fermi, which are there in the already operational, and they can start following the GRB. So you can have a really true multi-wavelength coverage, for example. So what is ECLAIRS? So it is not this. It doesn't mean that. It's not the toffee we eat in India, but it's called lightning in French. So it means that. So just keep in mind, random just a joke. So it's, as I said, a wide field coded mask imager, hard X-ray or soft gamma ray, you want to call imager, and its primary objective is to detect and localize GRBs on board in near real time, for example. And it's one of the feature also is here. It's a little bit detailed maybe, but it's that it will go down to 4 keV. So it is very important to detect GRBs which are at the high redshift or which are faint or softer, and they have a softer spectrum, so that most of the imaging are at lower energy. So this is something which is not at the moment. The SWIFT doesn't offer this. For example, it has a little higher and the low energy threshold is higher at the SWIFT pack. So let's now I'll go with the little bit of detail. Yeah.
Can you go back to the previous slide? I had a very trivial sort of a doubt there.
Yeah.
So what exactly is slewing?
So slew is basically satellite moving to some target. So the motion of satellite from one target to another target is called slew. So you have a target, you have a telescope which is pointing at X direction, and then you want to move the satellite or the telescope towards another direction so that that other direction is in the center of the field of view, for example.
So it's basically changing the field of view from one object to another.
Yes, more or less. So ECLAIRS, for example, will have very large, as I think it is mentioned in there, it has a very large field of view. So even like not like, even if there is something very 10 degrees to 20 degrees off axis, then you still detect it, but it will not be in the field of view of MXT or VT because they have small field of view. So you want to go on to that part. So that motion is called slew. Or any satellite motion when you move the satellite from one object to another object is called slew, at least in space telescope context.
Okay, thank you.
So what kind of an orbit will SVOM have?
Yeah, it will have a low Earth orbit. I will talk about it a little bit in later details. Yeah, so good question. Actually, it will have a low Earth orbit, about 620 kilometer altitude.
Also, in the previous slide, what is the VHF network like?
Yeah, so this is a network of antennas spread across the world. They are setting it up for SVOM, and they are like very high frequency. Basically, there's no more to it. They are just very high frequency antenna at some frequency. I don't know exactly what is the frequency, and that is to transfer the ECLAIRS trigger very rapidly to the ground. So that the idea is that ECLAIRS, like the satellite, will always have one station in the field of view, at least the VHF station. So you can transfer the trigger information quickly, because downloading the data and other things, you need the telemetry, which can be only done by like large antennas with a lot of dedicated set of antennas. Basically, you have the telemetry stations of each space institute of space organization. So, but these VHF networks are just to transfer quick data about the location, the significance, and other housekeeping parameters. What was this thing, so that you can quickly locate move the telescopes on ground.
Yeah. Okay. Thanks.
There's a question in the chat box by Sumant Atraya. So if a GRB lasts for 30 seconds and slew takes 5 minutes, so how does that work?
Okay. So it will. So there are two things. When it is slewing, so the gamma ray emission, it is if the 30-second GRB has a peak at, like, let's say after 2 seconds, 3 seconds, it will get detected. For example, after 2 seconds itself, the ECLAIRS will say, oh, there is something, and it will start the slew immediately within like next 5-6 seconds probably. And in that case, ECLAIRS will still detect the radiation, and it will not do imaging or anything. So it will just detect the radiation from that, because 30 seconds you have the gamma rays coming, and it will still in the source will be still in the field of view. But in that case, mostly the optical, the afterglow emission is not of significance at that time. You might have optical emission in that phase, but it's not always possible. So basically, the trigger part will be shut down. You will not ECLAIRS will not keep on detecting something all the time. It will just say, okay, I have detected something, now the satellite is moving, but the data acquisition will be still coming. It will be still active. It will just, the trigger will not be working. So I will explain what the data is in a few minutes, what actually you observe, for example, in such cases. I hope that answers the question. Anyways. Okay, so yeah, so let's see now. Where was I? Yeah, so how does you detect how does ECLAIRS detect this radiation, or like GRB photons, and how does the data look like? So what do we get basically when you see that? So let's say start at first look at the detectors. So here is a photo of the integrated plane of the ECLAIRS detector plane. This is final, like a flight model. This will fly basically in 2 years time. So it has like about 200 detector modules in this arrangement, 10 cross 2. So each detected module is basically 8 cross 4 grid like of pixels of 4 cross 4 size dimension, 4 cross 4 length, like in the, and 1 millimeter in thickness. So they are made up of this CDT, this is cadmium telluride semiconductor. It's a mixture of the two. And what you have is so if you look at each pixel, for example, it is something like it's a cartoon picture. So you have basically two anodes, like, and then like a cathode and an anode, and then you apply electric field within the pixel. So these for example, these gold color things are these have these cathodes, and then you have another like the anode at the bottom, for example. And what you do is so when so you apply the electric field, and when a gamma ray photon or X-ray photon hits here, what it does is that it usually kicks an inner shell electron of the material, like the cadmium or telluride. So then this electron is so it absorbs the photon, it ejects the electron, which has some energy. Then it goes onto the another atom and ejects some outer electron, probably. And then there is of course there is always a possibility that there is an excess energy which then lost to the lattice, or it is distributed among the other atoms. And then you have this then the outer shell electron, the original atom, comes back into and fills the gap, and you can have a X-ray lower E photon coming, which also again interacts with another atom, and again it ejects an inner shell electron, which again elects outer shell electron. And then in this way you have a cascade of this chain, and you have this electron and hole cloud. So, and as you know that this is a semiconductor, you have these valence band and conduction bands. Most of you probably are aware of this, at least the basics. So then ultimately this semiconductor becomes a conductive, so you can have a current through that, so which was not possible earlier because of the. And then you have the electric field, so that these charge carriers, as you call it, they start to move. So what does it do is that it creates a pulse basically at the end. So if you measure a voltage across these if you across these two plates, you will have a pulse which is like something like this. And this pulse is usually proportional to the number of like the charge pairs or number of charge carriers created. So which is, let's say, n0 or some kind of thing, and which is then proportional usually to the energy of the photon. So you are technically, the voltage is kind of proxy for the energy of the photon. So you can do the electronic readout, like you have the electronics to read this voltage, convert it into you digitize it, and then you store it in there. So what you get then, in typical case, at least in the case of ECLAIRS, which operates on something called a photon counting mode. This is what it means. Like then there are other modes of operations also, but not go into details. And so what you get is the time. Look,
there's a question in the chat box.
Yeah.
So Sayan Yogi is asking regarding the previous question. I think he's referring to the question that if GRB lasts for 30 seconds, how do we observe them if fluing takes 5 minutes? So he's asking regarding the previous question, is there any radiation which follows GRBs?
Yeah, so as I explained before at the start, that you have the prompt emission and then you have the afterglow emission. So the afterglow emission is at lower wavelengths at the same position. So you have the gamma ray burst in the gamma rays, then you have the optical or radio or infrared, like more or less in almost entire EM spectrum. You can see that. So I think the intensity and all varies, of course, on the environment of the GRB, like what kind of galaxy is in and what kind of material is it, and etc. So you have the intensity in each band will vary according to that, but you have it in more or less in all the lower energies. So you want to observe that. That's why it's loose. So you have this X-ray telescope or visible telescopes going on to that point to observe it at lower energy. So that emission is usually anyway after, say, few hundreds of seconds. Yes, like So because it's the jet emitted, and then you go to that emission, for example. So when the jet starts to interact with the interstellar or other medium, then only you start to get this afterglow emission. So there is a delay always in between the actual GRB and the afterglow. Okay, so yeah, after so once you read this detection, what you get usually is event, which is then called as, which is basically the time of arrival of the photon, because you record the time when you collect the charge, and which is approximately same as the arrival time of the photon. And then you have this something called PHA, which is the pulse height amplitude, which is basically this voltage created. Then you have the X and Y, basically the pixel X and Y, and you can arrange, you have the named, we have named the pixel in certain order. So you have the position basically. So you have like you basically have the time, energy, proxy, and the position. So if you record like number of photons, multiple photons, for example, even at a same energy, you will not always get the same PHA value. So this is something which is intrinsic to the detectors, for example. So, for example, what you get is something like this. So this is a spectrum of a radioactive source used for calibration. So what you see here on this thing on the x-axis is the PHA, which is the channel or voltage created. You can see, and you on the y-axis is the number of counts. So you have this radioactive source, and you put a detector in front of it, and then you observe what you. Then you record what you get on the detector. So you usually get something like this. So now this doesn't tell us anything. It just tells us that there is a peak at this channel, and so basically some energy is there, voltage is created at this, and then on at other energies also. So one of the major aspects of instrumentation, for example, is this calibration, doing this calibration. So basically finding this relation. For example, what is this? What is the relation between this channel and the energy? So it's usually linear, but sometimes it can be different based on the detector properties. So once you do that, then you can transfer that information from channel to then into the energies, for example. And then if you notice that even if you input one energy, you don't have just a single peak. You have always a width, you have this tail, and then you have some other these things. So in this particular case, if you see that the energies at black values are typical energies of the radioactive source. So they are emitted by the radioactive source. So they are the intrinsic. So they are coming from the source. But if these two are, for example, are something called escape peaks, which are properties of the detectors, because causing from the fluorescence of the cadmium telluride, and then you have these residue. Basically, the photons are escaping, and then you have some peaks like that, and then you have this charge. This is like a tail kind of thing, which has a second order effects because of the detector itself is the carriers in the detector, the electron hole pair, they don't move very freely. There is always a resistance. There is some loss, and also you have such kind of properties. So characterizing this is something which is one of the aspects of instrument, for example, instrumentation. And this is something I have done I will talk about it later for my master's.
Sujay?
Yeah.
Sorry for disturbing. Can you go back a couple of slides?
Yeah.
The previous one, I think.
Yeah.
Yeah, this one. So if the radiation has to knock off the electron, there will be a precise value of energy for which the knocking off will take place, right? Even if there's slight excess of energy, then the interaction won't take place, correct? So I don't understand this point where the energy is getting leaked into the lattice.
No, I mean you have you have excess energy, so that the electron will it will eject it will eject the electron, and then you have some energy which is then has to go somewhere. So it is just lost to the lattice. You have, because if you have the very high energy photon, I mean if you have 10 keV photon and the energy to reduce, I mean like it's like, okay, wait, let me try to explain this. If you have 10 10 keV photon, and you have the energy to eject the photon is 9 eV, 9 keV. So you have 1 keV excess. So that excess has to be dissipated somewhere. So it's lost to the lattice because you eject the electron. So there is that one electron has some kinetic energy or something which has to be lost. I think that is what it means by here. Lost
Okay,
to the
thank you.
lattice.
Thank you.
Okay, so
Sorry, there's another question in the chat box.
yeah.
So Anuj Chaturvedi is asking, how can studying GRBs help us to study about strong and weak nuclear forces?
I'll come back to a little later at the end, maybe, because probably it's will disturb the flow of the talk at the moment. Is it okay?
Yeah, no problem.
Yeah, because I'm already into detectors at the moment, so it's a little confusing. I'll come back to it later a little bit. Also, I don't know, to be honest, I also don't know exactly details about that. It's not really my field of expertise, but I can try to answer some of the things, at least at the end of the talk. Okay. Okay. So, yeah, where was I? Yeah. So even if you did like, even if you, for example, shine one particular energy, you have multiple energies detected in the detectors in typical case. And so if you do this exercise for example, different energies, like here it is, for example, 59 and 13 and like other energy, but if you do it like other energies, you get something which is like this, which is called the response of this detector. So for example, in the x-axis, it's shown is the energy. And so if you incident energy, so if you, and the y-axis is the energy measured or the channel. So it's the same, is more or less equivalent. So here you see, if you incident like energies below 30 kV, you have only one peak, which is at more or less at the same energy. For example, it's here, and it has to be at the same energy. Sorry, and then if you increase the energy, you get all kinds of weird stuff, like counts at different, all sort of different energies. Like you have like a continuum here, you see two lines. For example, if 100 kV, you have a main 100 kV peak, and there is some energy which is probably because of the tail, which I was talking about. Then there are these two peaks, and then another. So all this basically is very like, this is what a GRB also would do. Like a GRB photon also would not always create a one particular energy at which it is. It can create events, for example, at different energies, and also you need to do all this calibration and need to understand the detectors, how it works. So there's something which is intrinsic to the instrument and the detectors. So for example, this translates into the something called its effective area. So if you see now, if you take this vertical cross section like of this, like if you see that at given this cross section, so if you are given incident energy, what is the total counts I get, like this point and this point, what are the total counts I would get? So if you plot this in the plot, you will see something like that. So something like this distribution. This is for ECLAIRS, and this basically gives the efficiency of the instrument against the energy. And so, or you can convert it into effective area by multiplying by the total area of the instrument, which is about 1000 centimeters square. So you can see it is never one. It is something which is weird shape. And this is with the mask, so the red one. So the mask also attenuates more the X-rays if you put a mask, which I'll come to it later in a while. So this effective area even lesser. So this is something which is important to study the sources or GRBs using, like when you detect the GRB photons, all this is important to go from what you detect and what you get from the instrument and what you actually observe to infer the properties of the sources or the the GRBs or any X-ray sources for that matter. So now with this with the detectors, now I will just speak quickly about water coded masks techniques. So how does this coded mask imaging work? So it's basically It's very simple technique like the pinhole camera actually. So what you have is a mask with opaque and transparent elements, and you have a detector which is sensitive, which is position sensitive, like the ECLAIRS detector plane, which is pixelated. So if you have one source on the top right here, you can see like it will cast one particular shadow here. If you have another source, it will cause some different shadows. So if you have two sources at the same time, you will have two different shadow patterns, usually overlapping. And in these shadow patterns, you can invert these patterns, and which is done by something called process called deconvolution, and obtain the original source position. So here, for example, on this right, I have given the ECLAIRS, shown the mask of the ECLAIRS, which is placed on the top of the detector in terms of the pixelated plane. And here are some properties of the coded mask, which are like you have the angular distance from the center of the field of view, which is more or less tan inverse of this L by H. And the angular resolution is more or less equal to the mask. M is the size of this mask element, basically size of these elements, divided by the height, the detector mask distance. And this coding process, basically you can actually describe this mathematically such that this detected pattern, like detected counts in each pixel, are basically convolution of the source intensities, like source counts in the field of view, which is this total field of view. You can pixelate this field of view, for example, in details you have to split, and then convolve with the mask pattern and with some flat background part, which is there from other types of sources, which are not coded, or other background noise or something. So it is a very simple definition. I'm not going into details of that. Can be a talk by itself. So I'll just show quickly what does it look. However, so here is one simulation of ECLAIRS itself. Though so this is the detected plane of this is the detected shadogram of ECLAIRS. So basically, this is the counts in the detector pixels when on a source from the top is shined. And if you deconvolve this, what you get is something like this. So there are two subtleties here, that this is in the detector pixel. So there are 0 to 80, 0 to 80. So there are 6,400 pixels, for example, for ECLAIRS, the detector pixels. And these is in the sky pixels. So basically, it's the sky which is divided into pixels because you want to localize the source and get the position. So you can see the source was here, and it casts a shadow pattern which is something like this. Now, if I change the source position, basically you'll get some different types of shadow pattern, which then will, for example, is for this kind of position. So now you can see here the entire detector plane has some counts, and here, for example, there is nothing here. So there's probably nothing has shined here, for example. So this is one of the intrinsic property of the system. So basically, if you plot the efficiency of detection of the photon, of the directions, for example, if you get something like this. So in the center of this field of view, you have the maximum efficiency. You have all you will always will not lose the counts, and as you go from the field of view away, the efficiency goes away, and you will not detect all the source counts which were incident on the mask. So this is something also which is important part, this kind of simulations and studying these things to study this system and how it impacts on the performance of the detection of the sources. And this is something also comes from the design itself. So you have to compromise things in terms of when you design the instrument, for example. And this also holds true for the detectors also, like some things you need to compromise here and there. And so right till now I talked about only the ideal case. Like I was considering, for example, here there is only one source and there is nothing else there. But in reality, you have another additional problem, that is that there is nothing idle and you always have a background. It can be of multiple types instrument or something. So, and especially for a wide field instrument like ECLAIRS will suffer highly from the astrophysical background, which is from the which are the photons coming from the sources other than GRBs or astrophysical sources, even for that matter. So this is like a few of the major components are these 6, you can say. One is the cosmic X-ray background, which is generated by the incoming, which is generated by the diffuse distribution of AGNs. So the AGNs which are not resolved, and so they appear as the emission is coming from everywhere. So the emission appears to be isotropic. So this background is more or less isotropic. Then there is the reflection of this CXB from Earth atmosphere, and as I said, the SVOM has low Earth orbit, so this is very prominent also. And then you have the hard X-ray emitted from the Earth's atmosphere. So these are generated by cosmic rays hitting the Earth atmosphere and creating X-rays, and they are coming back scattered towards the satellite. So, and then on top of that, you have some particle background, which is this something which is most prominent for low Earth orbit satellite is the South Atlantic anomaly, which is these trapped particles near the South Atlantic Ocean and near like South America. So you have the excess of charged particles because the anomaly in the magnetic field of Earth. So you have like electrons and protons, and whenever the SVOM will pass through it, it will bombard with the particles will be bombarded onto the satellite. And then you also have, of course, the cosmic rays themselves hitting the satellite. So that creates a lot of noise. And then one more thing is this is like instrument and satellite body activation is like that. These particles, whenever they hit, they generate the radioactivity in the materials of satellite itself. And then they decay at longer delays, and then you detect these X-rays from them or even particles, secondary particles from them. So one of the part of my thesis was to do these simulations of this background. And so in this green, the backgrounds in the I've written green, which is what we did the simulations. And rather that is what I will talk about. We also did simulations for charged particles in SA. And then this cosmic ray and the cosmic ray and albedo particle is something in the process right now. And then the simulation of body activation is a little bit difficult to carry because you actually need to know the impurities and how they respond. So it can be only done after the satellite is launched. So another additional problem for SVOM is that it has a lower Earth orbit and it will have Earth in its field of view because the satellite will not move when the ECLAIRS is looking at the Earth. So if you see this orbit, so at once per orbit, the Earth will pass in the field of view of ECLAIRS, for example. So this causes problem because this not only have higher background, but it also varies the background. And something like this is known before, like also this like this is from another mission called HETE-2, which was in 2000s. And you can see that there is this variation of the counts, which is basically the photons detected as a function of time, counts per second. So this like light curve. And you can see that there is this background, and also top of that, you have this source variation. So there is this one particular astrophysical source called Crab Nebula. So it is setting here, then this Earth is in the field of view, and then it again rises. So you have this kind of variation. And in reality, on top of that, you will have a GRB. So detecting GRB, it's something you really need to know the background very well, and you need to model this to have some performance test done with the instrument. So what?
Sorry, I have a question. Does gravitational lensing also have an effect on the like measurement of location of the source of GRB? Because GRBs often also come from distant regions, right? So,
yes. So there are So this is a good question. There are what you say. Theories, theories are there that we should detect gravitationally lensed GRBs. So basically, they should have the exactly same spectrum or light curve because they are coming from the same object, but that should be deferred by the location. Basically, I mean the location should be different. I mean, and also it depends on the location will depend on the lensing mass, for example. So, but there is no yet any detection of gravitationally lensed GRB. So there are theories that it should affect that we should, for example, have two GRBs detected at different times, like 2 years, 3 years apart, but they should be the same GRB, but they are lensed, for example. Yeah, there is no yet any concrete observation. There are efforts going on to look into archival data, but it's extremely difficult because the GRB light curves are very notorious, like they are very different shapes, and also it's not very simple to look at it and say, oh, there are two same GRBs or something like that.
So apart from the experimental difficulties, are there any in principle or theoretical reasons why we have not yet observed any of these gravitational lens GRBs? Or is it just
No,
because
no, there's no theoretical problem. It's just experimental. You need to be looking at the same part of the sky, almost same part of the sky. For example, I mean, your lens GRB probably would not vary more than few degrees, I would say. I mean, I don't know exactly the numbers here, but rough guess, I think degree is a degree or 2 degrees. So you basically have to be looking at the same part of the sky in 2 different times, okay, at the same sensitivity, more or less. So that is something extremely difficult to do because you don't have that large field of view telescopes yet. I mean, these also have, ECLAIRS has like 90 cross 90 field of view, but 2-star radian, but it's not enough. I mean, it's sky is 4 pi, so it's like still only 1/6 of sky or something. I think it's even less, I think.
Okay, thanks. There's a question in the chat box by Sayan Yogi. Is it possible to train neural networks, that is, use artificial intelligence to detect GRBs amidst any given background?
Yes, so there are efforts going on. There are, I think there was a paper. I mean, I think there was one paper by Astrosat CZTI that they tried to train neural networks to see that. But I'm not aware at the moment to anyone who has done it with a robust this thing. I mean, this is something, again, is the background is very instrument dependent and all. So yeah, but I mean, theory, yes, possibly yes. In future, probably it will be possible in few years, probably. So it's my guess.
Also, like just one more question from my side. Sorry for hogging the mic. So, do we observe any sort of dispersion curve in GRBs? Are gamma rays dispersed?
No, they have very. I mean, the interaction. I think the interaction length is the interaction with the surrounding medium is not that what do you say? It's not strong. I mean, they penetrate easily. Like, so once they are emitted, they usually reach directly. There is no, they hardly interact in between, like between any, the electron densities in between are usually very low for gamma rays and all to interact heavily. You of course have some attenuation, this probability, because you have larger lengths, but it's not gonna cause any trouble with this. So there are observations of different the different energies arriving at different times, but I think they are more associated with the emission site itself rather than the dispersion part. So I'm not so sure about this, but I don't think so prima facie.
Okay, thanks a lot.
Okay, so as I said, coming back to this, so it's important to simulate and it's important to study this background. So what we did is to also, one of my part was to, we created this model, mass model of the ECLAIRS. Basically, it's the actual chemical and geometrical model of the instrument, which can be created in software called GRBs. I think Arvind talked about it a bit in his talk. And so you can see here, this is the model, this computerized model. And then as part of this is we developed a method which was something which is new, that to generate this background dynamically. So the software cannot generate this background variation in the time. It just gives, you can just shine photons and it will give you the interactions. So what we did, we take these interactions, store this in large in database, and then write an algorithm to generate a time-dependent background. And from that, we can generate a time-dependent data for ECLAIRS, for example, and simulate it basically. And so we studied 3 components: CXB, reflection, albedo are more or less the most prominent ones for ECLAIRS. So when you do that, for example, this is what we can simulate, is that to how the ECLAIRS background varies as function of the time. And here is what I've shown, that you can see this variation based on the Earth passage, as I saw, similar to the other actual data for the other mission. So it is something similar, but of course it's not exact same because different instruments, different orbit, everything. And you can see that there is a huge variation in this background. And on top of that, in reality, you will detect a GRB. So these kind of simulations are important to do these studies before you launch them. So this is a light curve of entire detector plane. But if you just look at the detector plane itself, if you see, there is an impact on that also. So here, okay, I forgot to put the captions. So here, for example, here is the detector plane in this part when the Earth is occulted. So you see like very low counts. Then you have this when the Earth is waning, like it's going out of the field of view. Then it's with the completely out of the field of view. You have like a large background. This is from mostly from the CXB photons, and then it has another effect. So this is very important to subtract. For example, in the coded mask, I showed this B component, background component. So it has to be subtracted properly to get a good location. Otherwise, you will end up in the noise problems and limitations on localizing the source. So what additionally you can do with this is also to generate a complete data. So that is what I did, as is like to generate a actual observing scenario. So here is, for example, one orbit which has a crab in the field of view. So you have this crab rise, when the crab comes out from the Earth shadow and in the field of view of ECLAIRS, then the count suddenly increase. And then I have simulated a cartoon GRB here to show that how a GRB would detect, how will be detected and seen in the count rate data. And then you, for example, if you image this part around this thing, you will get something like this. There is only crab in the field of view, the GRB goes and then goes out. So this is in the loop, so it's running like how the transient GRB would look in this image. So here what I plotted is something called signal to noise ratio. So it's not the counts image, it's not the total counts observed on the image, but the significance of the counts basically. So to observe the GRB, you need to have some mechanism. So we have this onboard trigger I talked about before, that it will detect in near real time ECLAIRS. So for that, it has like dedicated algorithm which is coded in the hardware, which is on the satellite, which will be in this kind of box. It's called a UGTS, called like a scientific processing unit. And it will have two kind of triggers. One is count rate trigger, which is for shorter time scale, which will monitor the count rate, which I showed, like there is a bump like this, then it will say, oh, there is something here. And then it say, okay, then we will we'll do the imaging and find the location of this. And then it will issue this ECLAIRS trigger, which I talked in the first slide, if you remember that will be sent to the ground, and then the satellite will slew and etc. etc. And then simultaneously, for longer time scales, you have the image trigger, where it will just do this image slices every 20 seconds, and then build a higher time scales and look for a new source in the image itself. So just doing the image. So the combination of both, we expect to have transients or GRBs from 10 milliseconds to 20 minutes. So I'll just give a quick summary towards the end. So I said, like, GRBs are extremely powerful explosions in the universe, and they are like important for various astrophysical and physical studies. But they are difficult to detect because of their short-lived. They are isotropic in the sky, and also the high energy radiation is usually difficult to detect because of its less interaction with the matter. And so also on top of that, you need multi-wavelength coverage, because the emission is in high energies as well as the optical wavelengths, or at lower wavelengths for that. So you need something which has everything. So SVOM will try to do that, like has dedicated sets of instruments. And the ECLAIRS, which is the primary instrument on board SVOM, is important to detect and localize GRBs in near real time. But it will at the same time will suffer from backgrounds, high background level, because of its wide field of view and other reasons. So we need to simulate these things and analyze it on the ground before you launch, and see what to expect basically from the instrument. So these kind of studies are important, for example. So with this, I'll stop talking about ECLAIRS itself, and I mean like this thing, and I'll go into quickly through my research journey through IISER, which is something everyone is doing here in these talks. So first, I mean, I always was interested in astrophysics when I came, like when I joined IISER. I mean, that's one of the reasons I joined IISER. I wanted to do astronomy, like to do science, to do research in pure science. So as a first project I did in my second year winter break, and then following summer was in NCRA. It was on radio astronomy. First I started with just an astronomy, this reading project in the December of like my second year, and then I took it up into summer when I did actually data analysis with GMRT image, and tried to study some AGNs. It was very short, but it was good experience for to learn actually like coding skills, basic, how to use data, how to do like use Linux computers example, for example. Then I shifted in my third year December, like to do something in optical, where I learned optical image processing and all. It was a short project again, just 1 month. It was a good experience again, and I was at Aries in the observatory. It's really nice place. You can go if you get time. Then in my third year, fourth year summer, I attended like IUCAA summer school, which was good to give me actually the introduction to almost all aspects of astronomy. It was like 1 month course with short lectures on many types of astrophysical and astrophysics and theoretical and observational both. And this is where I actually got interested in instruments more. I mean, then I did a project there itself with Dr. Varun Bhalera, who was there at that time. He was a postdoc there. So that project I did as to do the prototype test. So what we did is to test the prototype of automating a telescope to follow electromagnetic counterparts of gravitational waves. And now this is actually a telescope as a Growth India telescope in Hanle. I think Arvind talked about. And this project, actually a lot of IISER students were involved. I was the one who first was involved to start with. Then there was Sumit who did this. Atharva is the same batch. Then Arvind worked on it, and I think Varun Shrivastava, my junior, he also did something about it. It was very IISER IUCAA project at that time. A lot of IISER students involved in that, and so it's good that it's actually realized now. So this was very fun for me. It gave me actually hands-on hardware experience to actually control the telescope in IUCAA, which had like a small telescope, like with the mount, and write this client software, client server architecture, work on codes, and as well as hardware. So it's really good for me. And then for my master's, I shifted a field a little bit, and then went into X-rays astronomy, and so there I worked on calibration of detectors and simulations of it. So where I did these simulations of LAX-PC using GANT4, and also simulations of something called Polix, some mission called Polix, which will be launched soon. I don't know when. I think in 1 year time. So here it is, the instrument. It's dedicated for studying X-ray polarization of sources like black hole binaries or neutron-star binaries, X-ray binaries mostly. And then after that, I did 1 year JRF before applying for PhD, and it was at IUCAA and IIT Bombay, and worked on the AstroSat mass model to create these GANT4 simulations. This also, I think Arvind talked about a little bit in his talk. So overall, yeah, so like last 6 years something I worked on instruments. Like then after that, I joined the PhD to do it because works on ECLAIRS. And so last slide before I stop is something which is like, I had some questions last time asked, like how to go into instrumentation. So some quick thoughts on my thoughts at least. So what you need to go if you want to go into instrumentation. So first, I think is essential is learning coding skills. Mostly Python or any is okay at the beginning. It's more or less important. Then of course you should start with exploring basics of astronomy. So you start doing observational astronomy projects. which would strengthen your astronomy basics, because IISER doesn't really have any, I mean, only has one course, I think, in astronomy, 1 or 2. So that is not enough. So this is important to do, or attend schools like one in IUCAA and also, which gives you exposure to a lot of fields, which is really good. And in terms of coursework, maybe in particularly curated to IISER is like you can take courses which are oriented towards experiments or like that, like electronics or physics labs. I think they were very important for me. I enjoyed them, physics lab, and it gives you the sense of doing experiments and or the real problems you can face, for example. And one thing which is important is maybe you can, if you want to do a project while in IISER, you can try to do a semester-long project in IUCAA and NCRA, which is related to instrumentation. And I think 4th year is ideal for this. It's good for it. You can take it as a course project and then get a grade for it also, so it reduces your coursework and also fun. This is what I did in my 4th year actually. Both the semester I took the project for prototype testing was my course project. And one thing which is that don't do my mistake, which is I have been too much doing instrumentation too much for last 4 or 5 years, and I'm ignoring doing science actually. So like analyzing data and all, or actually working on like analyzing GRBs, and for example here in terms of like studying them, the science of them. And it is actually now I realize that it's not a good idea to do this, and because it can have like you can do instruments, but if you don't have you can lose the sense of why you are doing it at some time. So the balance two things out. Try to balance. For example, if you do instrument project in 4th year, then for your master thesis do something completely science, and try to balance out both things. So that's it. I think I've taken 1 hour, maybe. Yeah.
Thanks a lot, Sujay, for the wonderful talk and the very inspiring journey. And your advice was like very important for anybody who's interested in instrumentation and in general. So if people have questions, please put them forward or type them in the chat, and we'll take them.
So I will answer them.
Hello.
Yeah.
So I have a few questions. On the observations in the graph, sir, could you please take that slide? And the observations that were linear, that graph.
This one? Can you see the screen?
So that. Next one.
You can see the screen or no?
Yes, sir, I can see the screen. I was asking for the next slide.
This
sir.
one?
Yes, sir. Sir, so in this slide, why is there a y-intercept on the graph, on the linear one?
No.
When the incident.
Okay.
When the incidences are 0, why are the measured energy is not 0?
No. So this starts from 4. So there is just the offset here. There should be 0. The incident starts from 4 in a kV. So it is something around 4. So this is not 0.
Okay.
The range is just cut out. So it is no problem there. Yeah.
Okay, sir. And has there been a case where gamma ray bursts from 2 or more sources have interacted with each other? Has there ever been a case like that?
2 or more? No, I mean it is one. It is one source itself. So there is it is highly unlikely to find 2 GRBs at the same position. I mean it's at the same time.
Sir, but if something like that does happen, what are the theoretical observations that we can get? Theoretically, what observations will we get if something like that will happen?
I think it is extremely difficult. I mean, basically the gamma ray burst is what, a star exploding or the 2 objects colliding. So it's in they will have in one galaxy there is some neutron stars which collide and then they explode. So you will not have 2 objects at the same position, for example, doing that, because it will be again only one burst only itself in that case, for example.
But if
And
they are at two different positions.
two different positions at the same time?
Yes, sir. And if they interact, then and while in the path, while
Interact. Okay, so you mean
while the gamma rays are traveling, they interact from two different locations. They are traveling. Sources are at two different locations, and while they are traveling, they interact. I meant it like that.
yeah, I understand, but I think you will only detect the gamma rays from the two different locations, and the gamma rays going. So they are more when you detect the gamma rays, that means that the jet is pointing towards you. So all the gamma rays are coming towards you only. So if you are detecting two at the same position, that means they are not directed towards each other. So if you go onto the one source, for example, you will not see a gamma ray burst from the other source, because the jet is not directed towards that source, for example. And so you only detect the gamma ray burst if the jet is directed towards you. So because the emission is from the jet, so that has to be focused towards the Earth. So if that two goes, you will detect two gamma ray bursts at the same time in the image, or two different instruments, for example, at the same time, and you will have the two different events. And it might be difficult to, if it is detected by the same instrument, might be difficult to distinguish. It will be definitely difficult to distinguish between the spectrums, because the photons will arrive at almost at the same time or something, and it's not probably possible to distinguish which one is what.
If I may,
Yeah.
Sujay. So theoretically, if you
Thank you,
have
sir.
these two gamma ray jets interacting, which is very, very unlikely because they're very, very collimated, and both in space and time. So you have very, very localized jets, very powerful jets coming from a very specific area, beam towards you, and in a very specific time. But in principle, if you have these two jets interacting, you could have like pair production events, which might then cause electromagnetic showers that are detected on the Earth by telescopes like the CTA. But this is highly unlikely because you, like Sujay said, you won't have these events happening in the same time even.
Okay. Thank you, ma'am.
Okay.
Thank you, sir.
Don't say that.
Don't say sir. Okay, so there are some questions in the chat, right? How is the mesh designed for ECLAIRS? Are there some specific properties that the mesh should have apart from being aperiodic? Yes, I mean the first property, like the important property, is that it should be opaque to the radiation, and enough opaque. So of course you cannot have a complete opacity in the entire energy band, because at lower energies X-rays will be absorbed. Higher energies, they will be transmitted in any some fraction will be transmitted anyway. So you have this thing. So that's why tantalum is something which is high Z element, which is often used, so that it stops most of the X-rays in the band, at least, which is important for this kind of detection, which is about hard X-rays or soft gamma rays. And on top of that, is the pattern itself can be different. So it can be completely random, or even with the cyclic permutations and all. So it can be something periodic pattern also. But then you have when you do this deconvolution process, you have some kind of noise coming into the deconvolution. So it's a trade-off between what kind of noise you want and how can you design your mask. Also, the mask has to be I mean, at least in the case of ECLAIRS, there is no support. If you see this thing, just a second. If you see this thing, there is no support. There is only the support on the corner. I think you can see the screen, right?
Yeah.
So there is no support. So for example, at least in this case, the mask has to be self-sufficient to support itself. But again, different kinds of telescopes can employ different types of masks, and it also depends on how big your telescope is or something. For example, Swift has a very big mask, but the telescope itself is very big, and the satellite itself is very like, it's not a small mission, it's like a very heavy mission. So but again, it increases cost and all. So
there's a question in the chat box by Gurvit. Should I read it out?
no, I can. It seems that your second year you gained experience in image processing and coding in general, but in your third year you did work related to instruments. What led you to turn the instrumentation? Being a science student, wasn't it challenging? Okay, so as I said, instrumentation, I turned one aspect is because I always also enjoyed at the same time doing experiments like physics labs. First, second year also, it was very interesting for me. So experiment something was like something I was enjoying, liking. And then, as I said, when I attended the summer school, I attended the talks, and then there was this talk by Varun Bhalerao, and it was very good about X-ray instruments again. And it was somehow it's nice to build instruments, and I want to try that. And so I just approached him and started to do working on telescopes. And then once I started that, and I started enjoying that, so it was kind of transit. So actually, IUCAA summer school was very crucial in this thing, that to get all, because it also gave me exposure to different kinds of fields, and that also led me to decide what I don't like, in a sense that okay, I don't enjoy this much, that I don't know cosmology that much, but I like this more than that, and so it was good that way.
So I think we have had more than 1 hour. So if there are no more questions, I would like to end the recording. And I encourage everybody to stay back and chat with Sujay if you have time, Sujay.
Yeah.
So I encourage everybody to stay back and but I'll end the recording now. So thank you, Sujay, for taking the time out and giving this very inspiring talk.
Yeah, no problem.